In this movie, we're going to use a real-world use case to apply what we've already learned about modeling relationships. But this time, we're going to look at one-to-one relationships and instances. Remember, data modeling breaks down into three phases. First, you develop a list of entities or tables that belong in the data model. Next, you determine and diagram the relationships between those entities. And finally, review the diagram for correctness and consistency, and sometimes you'll revisit steps 1 and 2 when necessary. Here's another process description. Remember, when looking for entities, we want to look for nouns in our description. So why don't you go ahead and pause this video and take a minute to read this through. Using the nouns technique, we can identify entities as classes, teachers, students, and advisors. Each of these appear to be different, discrete types of data, and each can be described uniquely. Let's also make note of this section. A teacher can also be an advisor for a later reference. Now we have our entity candidate list, and these entities will eventually become tables defined in our database. But before they become tables in our database, we must first determine how the entities are related to each other. This is where we'll want to create an entity relationship diagram, otherwise known as an ERD. In any ERD, it's common to represent your entities as a box with the entity name inside of it. Let's move on to exploring the relationships between these entities, starting first with students and classes. We're going to use questions formatted within the one-to-many logic that we've been discussing throughout this title. For example, here the questions would be, can each student potentially have many classes? Yes, we remember in our description, students can enroll in as many classes as they like. Now, can each class be taken by more than one student? Yes, we also learned that classes are intended to have more than one student in them at a time. So what we have here is a many-to-many relationship. And if you recall from previous movies, the way we resolve a many-to-many relationship is by adding a third join table. We'll add a new table and call it students and classes. Now, when I'm naming a join table, I like to combine the names of the two parents, but if you'd like, you can name them something different, and in this case, you can call it enrollment as well. We'll then visually represent the relationships between each parent and child table with a line connecting each box. The double hash lines will be on the side of students and classes because that table serves as the many or the child in both of these relationships. Now let's evaluate whether or not there's a relationship between teachers and classes. Here are the questions we would ask in this case. Can each teacher potentially teach many classes? Yes. If you see in our description, it mentions teachers can teach many classes. Can a class be taught by more than one teacher? No, a class only requires one teacher. So this tells us that there's a one-to-many relationship between these two entities, with classes as the many. We'll want to represent this on our diagram. Now, in this example system, we've got something a bit different happening. Let's look at the relationship between teachers and advisors. Now let's ask, can one teacher have many advisors? Well, this doesn't fit because in this process description we saw a teacher can also be an advisor. So what we really have here is what's called a one-to-one relationship. And what that means is that a teacher and advisor are technically the same table. Therefore, we'll want to eliminate advisors as a table on our diagram. But there is a relationship between students and advisors. We saw in our description that a teacher can be an advisor to many students. So what this means is that we have to add another instance of the teachers table, but not a separate advisors table. That instance will act as the parent to students. We'll discuss how to handle instances in an upcoming movie. But first, let's look at our entire diagram with all the relationships in place. Now, although relationships are not drawn directly between the students and teachers tables, these tables are still related through a chain. For example, a student could enroll in a class that's taught by a teacher. Therefore, that student is indirectly related to the teacher through this chain. Now, once our relationships are in place, we can now determine which tables need primary keys and then foreign keys. But let's start first with the primary keys. We see the following tables acting as the one or the parent in our diagram. Students are a parent to student classes, so they'll need a primary key. And classes are also a parent to student classes, so they will also need a primary key. And teachers are a parent to classes, so teachers will also need a primary key field. Now, the advisor table is not actually its own table. It's an instance of the teachers table. For now, since we do not need an additional advisors table, we also don't need a separate advisor primary key field. Instead, we'll reuse the primary key field in the teacher table for that relationship. And now finally, the foreign keys. We apply our rule and see double hashes touching the following tables in our diagram. Classes are a child of teachers, so they need a teacher foreign key. Student classes are a child to both students and classes, so we need two foreign keys there, one for students and one for classes. But let's not forget our instance of advisors. Even though it's not actually a new table, the students table is still going to be a child to advisors. So let's make sure to add a foreign key for advisors to the student table. Going through these steps for each database you create will help you verify that each relationship that you have is going to be a one-to-many. It'll also tell you what keys you're going to need for each table. So there's a quick rundown of applying relationship design to an academic situation. Go ahead and use this example if it works for your project.